All right, now a bit about linear spaces in general. Okay, so a linear space, you could also call it a vector space if you like. It's really the familiar, or the spaces we're most familiar with. Okay, for example, Rn. So if I have two vectors in Rn, their sum also has to be in Rn. Okay, I also have commutativity of vector addition, associativity. We have something called a zero vector, so that when I add it to any other vector, I just get that any other vector back. I have the negative of a vector, or its additive inverse. So when I add the negative to a vector, I just get the zero vector back. And when I multiply a vector by a scalar, I stay in that space. I remain as a vector within that space. Okay. I also have something called a multiplicative identity here. So when I multiply a vector by 1, I get that vector back. Okay. And I have associativity of scalar multiplication and distributivity of scalars in vector addition, and distributivity of the sum of scalars multiplied by a vector. Okay? All these properties together make a space a linear space. That's when we can call a space a linear or vector space, whenever they have these properties. Okay? And also every vector space has these properties. Okay? So these are just formalizing things we already know, that when you add two vectors together, you get a third vector that's also in the space. You don't leave the space and suddenly go somewhere else. Okay? Just like if I scale a vector, I stay within that space. I don't suddenly jump to another dimension or something like that. Okay? So those are the properties of a vector space. And once we have that, we can think about matrices as maps, as linear transformations of that underlying vector space. And whenever we think of functions or transformations or maps, whatever word we're happen to be using at the time, we could start asking, what's the domain of that function? What's the codomain of that function? What's the range of that function? Okay. Notice here that I distinguish codomain from range. Okay. Technically, they are different concepts, even though they're often used interchangeably, not quite correctly. Okay. So the domain is the space that the function takes inputs from, and the codomain is the space that it yields outputs, where the outputs exist. Okay. The range is different in that it's the actual image, it's the actual picture of all of the vectors that the matrix maps to. Okay, so it's a slight difference, but just something to keep in mind. Okay, now when we are thinking about matrix transformations in particular, there's two spaces that we want to think of. One is the space of all vectors that get mapped to the zero vector. Okay, we saw that last video, how that might work. That's called the null space. And then everything else is called a column space. It's the image of all vectors under the matrix multiplication. Okay, I've got some questions here for you to try out, and we'll work through these when we see each other again. Let's just take a look at some of these concepts in action. Okay, so I've got this matrix. Let's call it A. Let's give it a label. So A, thinking of A as a linear transformation, it's mapping from R2, so it takes vectors in R2, and it maps them to vectors in R2. Okay, but now we want to see exactly how it maps it. For example, if any vectors in R2 get mapped to the zero vector. Okay, well, let's see. We can ask, are there any vectors so that when I multiply them by A, I get the zero vector? Can I find such vectors? Well, let's try it. So I'll put a vector of unknowns. I'll write my A, like this, and I'll write a vector of unknowns right here. And I'm going to set up this equation and see if I can get the zero vector after that multiplication. And if I can find a vector like this that gets mapped to the 0 vector, that's going to be in the null space of that matrix A. So let's actually do this multiplication. I've got 2 times V1 plus 3 times V2 is equal to 0, and negative V1 plus 2V2 equals 0 as well. So you can see I can rearrange this. I've got 2V2 is equal to V1. So I could rearrange it. Let's rearrange it like this. 4V2 equals 2V1. I wrote it like that so I can sub in that 2V1 into that first equation. Okay, and if I do that, then I'm going to have 4V2 plus 3V2 equals 0. Unsurprisingly, this means that V2 has to equal 0. Now, if I sub V2 equals 0 into here, for example, then I would get V1 equals 0 as well. So the only vector that gets mapped to the 0 vector is the 0 vector. So that's going to be the null space of this matrix. It's simply just the 0 vector. No other non-zero vectors get mapped to the 0 vector. Okay. Unsurprisingly, that would mean that all other vectors get mapped to vectors in R2 somewhere. Okay, so it doesn't collapse the space down. There's nothing's going to 0 that doesn't belong at 0. And everything else is going to go to some other vector in R2. Okay, this means that the column space, or another word for that is the image of the matrix, is all of R2. Okay, there's nothing that kind of disappears under this matrix multiplication. Now let's look at another example. This here. This is, again, I'll call it matrix B. Switch it up a bit. B goes from R2 to R2, just like last time. But now I want to see, perhaps there should be some vector that, when multiplied by B, will go to 0. Let's try it out. You can kind of suspect that we will get a non-zero vector. Why should that be? But let's actually try it. So I want this to equal 0. When I write it out, I really only get one equation. Right? If I multiply this next one, I would have negative 3v1 plus 4v2 equals 0. And so I can multiply through by a negative, and I would just get this equation. Okay. So what this is saying is, anytime I have a vector where I have v1 equal to some value, so long as v2 is 3/4 of that value, then this will get mapped to the 0 vector. Okay, so any scalar multiple of this vector is going to get mapped to the 0 vector. You know, we could try it out. I could take 4 and 3, the vector 4 and 3. So if I take some scalar multiple of this, which I'm going to use as 4 and 3. When I do this multiplication, I get 12 minus 12, 0. I get minus 12 plus 12, 0. There we go. So this is going to compose the null space of this matrix. Okay, so this is in the null space. And I can find all other vectors in that null space by just looking at the span of this vector. So if I take all scalar multiples of this vector, that's going to describe the entire null space. That's all vectors that are getting mapped to the 0 vector. Okay? And the column space is going to be all vectors that don't get mapped to the 0 vector, the image of all those vectors. Okay? And that's something we'll talk more about in person. Okay? I encourage you to try some of the methods that we saw already to answer the question for this here, what the column space and the null space of that matrix are. And here's some more practice problems. But in terms of this topic, there's one kind of fundamental idea that I've been using already in this video. It's this notion of that nothing really gets lost under that multiplication. Okay, so I take a matrix, I'm going to multiply it by all vectors in a vector space, and I'm going to look at the image of those vectors. Okay, so perhaps some of the vectors are going to get mapped to 0. Other vectors are not going to get mapped to 0, and those are the only two choices. Okay, there's not like a third option where some vector, goes to some other space that we don't see in the image of the matrix. Okay, so that's what this rank nullity theorem is telling us. It says you have no choice. You either have the vector getting mapped to 0 or not getting mapped to 0. Okay, and those are the only two options for vectors in the domain of that matrix transformation. Okay, do you remember what dimension means? Go back and define this term. It's really just the number of vectors in a basis for the vector space. Okay, so it's the dimension of the domain. If we look at that dimension of the domain, what we have here is it's the dimension of the column space, so the stuff that gets mapped to non-zero vectors, and the stuff that gets mapped, the dimension of the stuff that gets mapped to the 0 vector. Okay, so it's saying that really, if I were to reword this, it says all vectors in the domain either go to the 0 vector or some other vector. And this theorem really accounts for all possible vector mappings under that one matrix multiplication. Okay, one last term here, that rank of a matrix. It's just another name for the dimension of the column space. So if you look at the image of linear space under the matrix multiplication, the dimension of that image is the rank of the matrix. Okay, so lots to practice here, and we're going to do some of that practice this week when we see each other live.